So we finished the voltmeter in the last one and discussed how we may not report 0.1 volts if we saw a fluctuating voltage. And now we go on to another analog meter. Well, once again, you sort of have to approach it and just sort of figure out how it is you want to make your measurement. So let's maybe use this very top scale up here to measure what this voltage is right here. So you got to get used to it. So this is 80 right here. There's 81, 2, 3, 4, and 5, and 86, 87, 88, 89, 90. So it looks like all these little marks in here are 1 volt. And so that's something you just have to get used to as you approach things. It may not be clear, but just don't be embarrassed or shy. Just take a few minutes to always familiarize yourself with whatever scale you're looking at. So I would say this one here is loosely speaking going to come in to be about 84 volts or so, but it doesn't quite look like it's on that line there. And of course, for some of these analog meters, there's something called parallax. Like if you were looking at it from the way left or the way right, it might even be worse. And so I would definitely sort of quote this uncertainty here to at least be 1 volt here with a lot of confidence here. Or since it's so close, I might even quote half a volt or something like that. But that's definitely what I would quote there. So maybe I am getting down on the instrument level, but I'm pretty sure just as I look at this one here that where that line is, and I can tell where the other lines are, and it looks pretty stable at 84. Might be as low as 83 or as high as 85, but that would definitely cover me in that trial. And you can sort of go to this scale here if that's the one that you wanted and see similar considerations here. Again, familiarizing yourself with a scale. You see a 25. Oh, let's see what we have here. 26, 27, 28, 29, 30. So see each one of these longer marks is a volt, and each one of these half marks would be half a volt. And so this looks like to me it's going to be 20. There's 26. Looks like it's 26 and a half or something like that, 26.5. And given that these little divisions in here are at least half a volt, I think I'm pretty confident in that I'm definitely not on this line. I'm definitely not over there. So I'd report this as 26.5 plus or minus 0.5 volts. I'd be happy going into a court trial, reporting something like that. Okay? So again, hope you see here that the uncertainties are not always the limits of the device itself. You have to decide what you're comfortable with. Even in quantum lab, writing stuff in your notebook or justifying a paper you may write someday or something, you just have to be comfortable with your uncertainties because, all right, you're not going to be in a court trial. That's the extreme case. Just something for you to think about, but you might be giving a presentation at a conference and someone might raise their hand and ask, hey, when you were measuring that voltage of your electron beam or something like that, how confident were you in that measurement you made? And you just come out and tell them, say, well, it was fluctuating, plus or minus 10 volts. And then the audience member can do whatever they want. They can yell at you for being sloppy if they want. They can commend you on the carefulness of your measurement, but that's up to them, and that's sort of how it proceeds. Each person has to sort of interpret this business themselves. So lastly, the way to think about it then is the classic case of the skid marks. You could definitely be on trial for something like this. You see the skid marks of length L, and the issue then is what was the speed of the car. You have to come and measure the friction, the type of weather that was happening that day, and all the stuff, the coefficient of friction between the road and the tires and all that sort of thing. But the way to think about it then is, again, you just say, well, the skid marks were length L long, but given all the environmental parameters and these sort of things, and you don't really know what actually happened, you would assign these skid marks some delta L. In this case here, again, what are you comfortable with? And that would probably tie into a little bit more than just you throwing a tape measure down here and measuring the length of the skid mark here. That might involve some uncertainties you might have in the coefficient of friction, depending on what the weather was right there, or the different types of tires, or even some uncertainties in the hill or speed or wind that day. I don't know, but all of those things would go into this. But the bottom line is, don't leave if you're not comfortable. Don't report something you're not comfortable with. So maybe you think the skid mark here is about 6 feet plus or minus 2 feet. Looks a little sloppy, but hey, whatever, you're doing the best job you can. And maybe there's some more analysis that you do that, given this uncertainty here, the speed of the car must have been 70 miles per hour plus or minus 5 miles per hour. I don't know exactly how all of these things would translate. We'll talk about that kind of thing. It's called error propagation, but this is sort of what you might conclude. You go into the trial, you say the car was going 70, but it could have been as slow as 65, could have been as high as 75. Again, you apologize, you give to them to interpret, you collect your $500 an hour consulting fee, and off you go. You've done your job. So again, the delta X here is really what are you comfortable with and what are you willing to defend. And you be a little careful, because if you're too large with all your uncertainties, you're going to look sloppy. So you don't have to be that casual and cover all bases. You don't have to do that. But also, if you're too small, no one's going to believe you. And I'll give you some examples of that when we talk about this week's lab. So anyway, so what that all leads into, though, with this business is this issue of error analysis here. And there's a bunch of books written on them. You can sort of see the theme of the covers. Here's a train that crashed through a wall. I think it actually happened. You can look it up on Wikipedia. This is another book that I used a long time ago. It's a very nice one here. You can just sort of see that the baseball is sort of traveling above the catcher's mitt right there. So there's some error involved, you know, the train crashing through the building and the catcher about to get hit in the face with the baseball. But this is sort of just the fun about this sort of business here. And it is sort of a neat, fun science. And I hope from the other videos I showed you, you will read this book on Taylor, because it's just a very interesting approach to science here to make sure that you're covering your bases with analysis in the proper way. Okay, so I will pick this up in the next video.